Yes, we can start. I mean, it's already 2:30.
Okay, so shall I start?
Yes, yes. Good afternoon, Professor Arnab and all the participants. So we are moving to the third session. That's the last session of thermodynamics. So yes, we can start.
Yeah. Okay, so yeah, I just closed my office door. So yeah, so I will start, but first there are some questions which I will answer to begin with. So there are two questions. What exactly a reversible process is in thermodynamics? How decay reversible, not zero, in an adiabatic expansion? Not zero. Achha. Can you quickly explain it again? Okay. Okay. So how decay reversible is non-zero? Okay. So I will just go to the slide. So I said like two situations. One in which I have a box where the gases are there, and the box, this is adiabatic wall. So this is adiabatic wall. So this doesn't allow energy transfer. So there is no energy can go in or go out. Okay. So in this situation, if I make a hole, a small hole, so what will happen is that the particle is going to escape and it will fill the box. So that hole. So this is an irreversible process. Okay, and since the walls do not allow any heat transfer, so therefore dq equal to 0. Now let's say this is situation A and this is situation B, and if I try to draw a PV diagram, I'll draw a PV diagram slightly bigger. So my pressure and wherever the pressure was, so right now pressure will be less and volume will be more. Yeah, something like some process happened from here to here. And that has happened through some irreversible path. So let's say this wiggly path is irreversible path. So one cannot calculate entropy from this path because the process is irreversible, and therefore we do not get. So at this situation we don't have dq reversible. We don't have dq reversible because we have not used a reversible path. From coming from A to B, we did not use any reversible path. So therefore we do not have dq reversible. Whatever we have is dq, and that is 0 because there is no heat is coming in and going out. And this is an ideal system. So your du is 0, dt is 0 because there is no change in temperature, and only dv and dp are changing, of course, and dq is 0, and dw is of course 0 because there is no work done. For free expansion there is no work done. Yes, Fatima, just 1 second. So now what I want to do is that I want to connect A to B through a reversible path. I need a reversible path to connect the same endpoints. These are these state points. A and B are state points. We need to connect these two state points, but we want to use a reversible path. And how do we do that? We have to construct completely different experiment. We cannot use this experiment at all. So we clone A, where A was something like this. Okay, and we need to go to B. So let's say A, this A has exactly same system as A, but then we need to do it in a very slow manner. We have to go there to B. We need to go to B in a very slow manner. So how do you do that? We construct a piston kind of thing. Let's say these are masses that are there. So we will remove the masses slowly. So volume will expand a little bit. When you have less number, then volume will expand fully. I'm just giving some example. So this is a slow and reversible. Slow and reversible. Now in this situation, the walls are not walls will allow heat to transfer, because otherwise it will not expand. So in this, we are getting DQ in. There are DQs coming in, and this DQ is a reversible DQ because we are doing it very slowly. So therefore, coming from A to B, we will have a change in DQ, which is a DQ reversible. And if it is done, okay. So why we need DQ? Because we need to maintain the temperature. So when the expansion will happen, if it is an adiabatic expansion, the temperature will reduce. But we need to keep the same temperature because A and B had the same temperature. So for that, we need to put in heat. Otherwise, that is not going to be possible. And so only difference is you have to understand that here dW equal to 0, no work done. Because there is no work done, temperature is not reducing. But here dW is non-zero because there is a work done. So temperature will reduce. Adiabatic process temperature will reduce. In order to compensate that, you need to put in heat. And that heat will give us the amount of heat, which is reversible heat, will give us a measure of change in the entropy going from A to B. And that's what we are doing. I hope this is clear, because if I go from here, this will wiped out. This will be wiped out. So this is like a temporary blackboard. Okay, so that I hope that that answered the question. We can have more discussions if required. If you raise your hand, we will have a discussion. Okay, so now second question was, can heat be converted fully to work in a non-cyclic process? Yeah, I said that cyclic process is not allowed. For non-cyclic process, it is allowed. Yes, it can be. I will just show you. So remember Carnot cycle. So in Carnot cycle, when you are going from first step to second step through an isothermal expansion, then the work done W, so here isothermal, right? So du equal to 0. Isothermal is basically for ideal gas CVDT, right? du equal to CVDT, and it is isothermal, so dt equal to 0. So du equal to 0. So your dq, so I said that, sorry, again, I will draw it, sorry. So PV, first step in the Carnot cycle is isothermal expansion. In this, since it is isothermal, du which is equal to CVDT, and again I told you this is true for only ideal gas, not for all the real gases. Okay, otherwise you have to write du subscript v. So anyway, so this will be equal to 0 because dt equal to 0. dt equal to 0, why? Because it's an isothermal expansion. Now since du equal to 0, we know that du equal to dq plus dw, and since it is 0, so your dq will be minus dw. That means whatever heat is going in will be converted to work. So in this step, full heat is getting converted to work. Full heat is getting, in fact, if you take this part of the cycle also, from here to here, let's say this is A, B, C and D. From C to D, you are getting full heat converted to work. So heat is going out, so work is done by the system. There also it is an isothermal expansion. So there also full heat which is going out that is work done by the system on that. Okay, so here what happened is so A to B is work done by the system is positive, work done on the system, and the C to D will be it's a compression process, work done on the system. No, it will be work done by the system and the heat will going out. Anyway, so it just depends on the sign. The reason that it is the full work done is not equal to the heat, because the now overall work done. So the work done will be the area under the curve. So first step, A to B work done is full area under the curve, which I can show using another color. So in the first step, this much work is done, and in the second step, only this much work is done. So the net work is done by the green color, which is this part, the area, this thing, and that is not, that is not equal to the Q in that is going in. This is Q in, so that is why you are losing in some amount of work, like that could have come from the heat. Okay, so therefore you are not getting a full conversion. Because why you are not getting a full conversion again? So work, I'm not, okay, just 1 second, I have to use this. So work equal to Q in minus Q out. That's it. And efficiency is work by Q in. You see, work by Q in. So Q in minus Q out by Q in. That's why it is not equal to 1. But in the first step A to B, work equal to heat Q in the first step, A to B. In the C to D step, work equal to Q out. So that is not a problem. So in one step it is not a problem. Only for a cyclic process is a problem. That is what you have to remember. Okay, so these two questions, if there are many more questions, so we can address that. But today we are going to talk about a new topic, an exciting topic, and that is statistical formulation of second law. So why we bring in statistical formulation, as also it's a part of the syllabus I have seen that is given, chemical thermodynamics syllabus. So the statistical formulation of second law is because we want to address this question, what I told you yesterday, that why entropy increase is favorable. This is what we want to understand, why it is favorable. That classical thermodynamics does not give an answer for. So we have learned that entropy is reversible heat change at a given temperature from classical thermodynamics. Therefore, it is essential that heat energy. I think there is something wrong in this sentence. Therefore, it is essential that heat energy has to be involved anyway. Then, how we relate the chaos and disorder or randomness, etc., to entropy? Because if I ask you what is entropy, you will say randomness, you will say chaos and all that, right? But we just saw that it is nothing but from classical thermodynamics that it is Q reversible by T. So how do you do that? So heat energy, as we have seen, is random motion of molecules. So we have seen what is heat. We have seen that heat is nothing but specifically multiplied by temperature, and temperature is nothing but kinetic energy, half mv squared, and v can be any kind of velocity. It need not be a directional velocity. It can be any motions that is there. So heat can be anything. Okay, any motions. So heat is proportional to temperature. Temperature is nothing but kinetic energy. I have written that already. Therefore, heat is some random motions, etc. Then how it gives us the time arrow? Then why we say that entropy increases with time? Like, how do we even relate to all those things? How do we know that for certain events like falling and breaking of an egg, entropy must be increasing? Now, this formula that we have learned, dq reversible by t, using that formula, can you explain? Can you explain using that formula? Just 1 second, just in the color. That delta S is whatever dq reversible by T and integration of that, let's say. So using this, can you explain that why breaking of an egg is an entropically favorable process? Or why the air will go out of the balloon and not come in? Why when you drop a ball, it never comes back to your hand? Or why when you put some ink in a glass of water, that ink you cannot separate anymore from the water? Can you explain using dq reversible by T? Of course you can in a very complicated way, but there is a straightforward way that I'm going to talk about today. So the answer lies that in fact the second law, that entropy of the universe is increasing, is true only on the average. That I told you last time also, that for some events we might find that entropy is decreasing, but on an average it will increase. Entropy is therefore a statistical outcome of certain occurrence. See, for example, if you go to a gambling place, like, there is a famous gambling place in Las Vegas of USA. So there are slot machines, and if you gamble there, you might win sometimes. But if you keep on playing, you will lose. Because the rule is set in such a way that house always wins. House means the gambling house will always win. They have set the machine. The machine's outcome are set in such a way that it is not a fair thing. 50% house will win and 50% other people will win. It is not set that way, because then they will not get any money. So individually one person may win, but overall house will always win. And if you as a person go on playing, then one day you will win, 2 days you will win, but third day you might lose. And overall loss will be more than the win. That's how it is set up. So therefore, that is the statistical average I'm talking about, that on an average, entropy will always increase. So the statistics is built not from the macroscopic systems like cricket, ball and egg. That's why it is difficult to explain using this dq reversible by T. Statistics is calculated on the tiniest, smallest ingredient of all species, atoms and molecules, in which we have to apply those statistics. So while it requires only smallest number of variables, NVD, I discussed 2 days back, last 2 days, to describe the equilibrium properties of a macroscopic system, it requires several variables. I told you how many variables would require to describe the bulk system in terms of atoms and molecules. Once we know about the position and momentum of all particle, we can obtain any property we want to. The subject which helps us to obtain that is called statistical thermodynamics or molecular thermodynamics. Meaning what? Statistical thermodynamics has two things. Statistics. See, statistics, if I tell you, what comes to your mind? Mean, median and mode. So you do some averaging, calculate median, calculate distribution, right? And thermodynamics. So some people also call statistical mechanics, where mechanics is motion and statistics is statistical outcome of it. So statistical outcome we are basically calculating using statistical thermodynamics or molecular thermodynamics. It is not possible, however, to know about the humongous number of variables and conditions. Therefore, probabilistic approach is used. So we are not going to look at each and every molecule, how they move and all. We will use probability. Although this approach will not give us individual detail, it will give us the desired property. Similar to quantum mechanics, where knowing the wave function, we can calculate the property and we don't need to know exactly how electron moves. So as long as we know the distribution of electrons' positions, we can calculate the average property. So it's like this. If I tell you that predict whether there will be rain tomorrow or not, you need several calculations to do that. You need to know pressure, temperature at different places in and around the region, several variables. You have to solve Navier-Stokes equation and all that to arrive at the thing that whether it will be rain tomorrow or not. But look at the weather around you. See how many days it rained in the past. See whether in this particular day it had rained for previous years or not. And then probably we can come to a probabilistic calculations that, okay, there is 60% chance or 70% chance that it will rain tomorrow. So that is the approach, this probabilistic approach we are going to use. So thus the connection between thermodynamics and statistical thermodynamics is probability, which will provide us the average expected outcome. We want only the average outcome. We don't want individual details. Let's see some example of how probability helps us to obtain good understanding and outcome. Right, so we'll return tomorrow that I already discussed here. So I'm just keeping it. Now, another important thing is that statistics is more accurate when there are more sample points. See, for example, if you toss a coin, you know that probability of head and tail is half and half. But if you toss a coin 10 times, you may get 7 times head and 3 times tail. Or let's say I'll do you 2 times. If you toss a coin 2 times, both the time you can get head. Then you will say, oh, my 50% probability is not maintaining because I'm getting 100% head. But your sampling point is less. You need to do 1,000,000 times in order to see that 500,000 times that will be head and 500,000 times it will be head. So for statistics, you need larger sampling, more number, and we have plenty of numbers because when we talk about 1 mole, we have 10 to the power 23 molecules. Imagine the number. A billion is 10 to the power 9. So we are talking about millions of a billion of a billion. 10 to the power 9, 10 to the power 9, and then 9 plus 9, 18, 18 plus 5 or 6. So 10 to the power 24 is a million of a billion of a billion. So imagine how big that number is. And that is the number we use to calculate the statistics. So it must be very, very accurate. That calculation will be extremely accurate. Now, I want to show you a work by Sharon Glosser. It is, she was giving a TED talk, so I've taken the video from there. And normally what we know that, if I ask you, what is entropy? You will say chaos or randomness. Now, this picture will clearly show you that that is not the case. Because here what is happening is, here you can see these particles. One is disk-like particle and the other one is ellipsoidal particles. These particles have no interaction with each other, which means that there is no energetic bias. But these particles they can arrange themselves, and if they are disordered, that means they are oriented in all possible directions, the color will be red. So that means if high entropy thing, or sorry, not high entropy, but less order or random structures will have red color. As in when the particles will get aligned or getting more ordered, it will appear to be green. Now, if I run a simulation, if the system wants to go to more disordered state, since there is no energetic advantage, it should remain red. But see what happens. Let's see what happens. You see, as and when the simulation progresses, the particles are getting more and more ordered, and they are getting green with time. So which means what is happening? The entropy must be increasing, because that for a spontaneous process, entropy always increases. So here also it is spontaneously happening. So entropy must be increasing. So she is Sharon Glosser speaking in the TEDx talk. So entropy is not disorder always, because in this particular case there is order, increase of order is happening, yet what we see that entropy is increasing, because spontaneous process, you already know entropy is increasing. So here also is increasing. There is a spontaneous process that is happening from red to green, but from disorder to order. So order and disorder is not associated with entropy. That is our common misconception, that entropy means disorder. So this is one of the clear examples which shows that it is not the case. Then what is entropy? So what is entropy? In my opinion, or in my understanding, the entropy is nothing but options, choices. That is my definition. Of course, it's not a book's definition, but this I want to understand in this way, that how many choices one person has. You can apply to in many different situations. For example, right now you guys have a high option to choose from, whether you want to be in a room and watch this lecture, or whether you want to be outside and watch this lecture, and you can be anywhere. But imagine it would be a live class happening in a classroom. Then your options are very, very limited. You have to be within that room. And within that room, you have to, listen to the class. So that would be a very low entropy situation compared to the situation in which you are right now, because you can be anywhere. So when you have more options, or when one particular system has more options, then the entropy increases. For example, that yesterday I was talking about the gas particles confined to half of the volume. Of course, it had less options that time because it only was confined to half the volume. It was only confined, let's say, to half the volume. But as soon as I make a hole there and the particles got access to all the volume, then the number of options increases and the entropy also increases, right? So one can understand entropy as simply as number of options. So this is the definition. If every system, if left to itself, will on the average change towards a condition of maximum probability. So that is what we understand as entropy. So if you leave it to itself, if you hold the particle here, of course they cannot go. Of course they cannot go. So you have to let it be free. Like if I force you to be in the class, of course you will be in the class. But if I tell you, okay, you can be anywhere, but you have to attend the class, then of course, I'm leaving it to yourself or the system to choose, and you will choose the most probable situation, which is depending on the situations, it will turn out to. Hello, Anjana, any question? Hello. Okay, fine. No question. So I'll continue. So please interrupt me if you have questions. So now I'll define microstate and macrostates again. So microstates are different arrangements of atoms and molecules. Like as I explained to you, what molecule on the top and the bottom of the glass when the glass of water in the glass of water case. And bulk matter is a macrostate, so which is defined by 1 liter, half a liter kind of situation. And again, position and momentum of atoms and molecules, and that is the number of variables in case of microstates, whereas for the macrostates, you can define by the macroscopic variable, which are number of particles, pressure, and temperature, and all that. So this is a movie which will not run here because I'm using iPad, but it's a movie of water molecule where water will go everywhere. Maybe I can show it sometime else. It's a simulation that we have performed, but I will show you many more movies, so many more animations. So I think this is fine. So it's not possible to know the position and momentum of each particle because they are huge in number. So probabilistic approach will be used. Now, where does it all start? So remember, when I was talking about second law of thermodynamics by Clausius and Kelvin and all that, it happened around 1850s and 60s. But see, soon after 1872, Ludwig Boltzmann from Austria, all alone came up with this statistical concept of entropy. And remember that time, even electrons were not discovered. Electrons got discovered in 1894. So people did not know electron existed. So they only knew atoms like, ball. And the statistics is built on that ball kind of thing. And if you see the derivation of black body radiation, that means Max Planck was working on understanding why the black body radiation is like that and not like what Rayleigh and Jeans kind of postulated or kind of derived. He did not want to, but he had to use the statistical concept of thermodynamics and apply to these distributions of these frequencies. When he did that, he got that. He knew what equation will fit the black body radiation, but he was not getting it by any other way rather than using the concept of statistical thermodynamics. And once he did that, he got beautifully that equation which gave the black body radiation. And when you use that equation as a constant factor, you will get the Planck's constant. H. And we know that that Planck's constant was subsequently used in 1905 by Einstein. And Einstein used that as a quanta of energy, H nu. And that H nu subsequently, 1925-26, gave birth to quantum mechanics. So you see, in a way, this concept of entropy is underlined in our understanding even of our quantum mechanics. And the probability that we are talking about, in the probability that you talk about as a postulate in quantum mechanics, they are called new probability, which Max Born gave. That psi studies probability density. That's Max Born interpretation, not even Schrodinger's interpretation. And that came, again, that was called a new probability, because the first probability, or the old one, or whatever you can call it, that is from statistical thermodynamics. So what is this famous formula which is imprinted on Ludwig Boltzmann-Domb? Is this formula, S equal to KBln W. W, what is W? What is so powerful in W? W is the number of microstate in the most probable distribution. This is a huge number of terms are there in this particular sentence. So just think that W is number of possibilities. That's all. If you forget this whole thing, just remember W is number of possibilities. And we need logarithm for some reason. I will explain why we need logarithm. Why not simply W? Why not S just proportional to W? Why logarithm of W? There is a reason for that. And KB, remember this KB, this makes this relation thermodynamic. Otherwise, even in case of information entropy, people use this formula. But KB is the one that connects this number of states to a real thermodynamic measurable thing. That is as powerful. So you see, everywhere these constants are coming up. In statistical thermodynamics, KB, in quantum mechanics, H, and those are all obtained from experiment. Now you can get a theory, but then you need one ingredient from experiment, because experiment is the observation, and that observation has to match with reality. The theory has to match with the reality through the observation. So that's where this whole thing comes up. KB one can always find out by fitting, right? But that ln W, why ln W? And why W at all? That is the question. Now, I cannot derive that, but so you have to take, okay, this is a postulate. See, some people ask me that, okay, how do you get that? So, you ask yourself, how do you get P equal to MF? How do you derive P equal to MF? You accept it because that's a postulate. In quantum mechanics, you accept Schrodinger equation as a postulate. You write it down and then you start. Of course, you can explain and things every term of it, but you write down that equation to start your calculation. Similarly, you write down this one to start your calculation on statistical thermodynamics. So this equation gave birth to statistical thermodynamics. Now, I'm going to show you, very small examples. Life is much more complicated than this. But if we understand this, then we will understand how to go about doing calculations for complicated system. So it is all about simple probability calculation. There are many books on that. And most of the probability problems, or many of the probability problems, can be understood using simple balls putting in a box. R balls putting in 3 boxes I wrote, but you can call it N box or whatever. Number of ball in number of boxes. But only thing is that the balls can be indistinguishable, boxes can be distinguishable. Both of them can be indistinguishable, both of them can be distinguishable, and balls can be distinguishable and boxes can be. So all 4 possibilities are there, and each possibility will give rise to new values of W. So again, I will show you one very simple simulation where I have 2-level system I'm talking about, right? So these 2 levels, one is right hand side box, another is left hand side box. So what happens is that I start with 2 particles on one side, and what is happening. Sometimes both the particles are coming on one side, sometimes each particle in one side and all. It's really erratically happening. Why? Because the number of particles is too small. We cannot calculate statistics based on this, right? So we start with n equal to 2, and then we are supposed to reach n equal to 1. N1 is the number of particles in left box, let's say. So let's say this is box 1. I'll just use a different color. Let's say this is box number 1. This is box number 2. So N1 is the number of particles here, and N2 is the number of particles here. And you know that N1 plus N2 is equal to N, which is the total number of particles, in this case 2. Okay. Point is that they are very small. Ideally, what should happen? One particle should be on the left, one particle should be on the right. But it is too small a number. One cannot calculate statistics based on small number. So sorry for that. I'll just remove this. So let's increase the number a little bit. Okay. I don't know what is happening. One second. Yeah. So now I have taken 210 particles, and I started with 210 particles on the right hand side. And see what is happening with time. With time, the particle is diffusing to the left hand side. See, there is no interaction energy here. So no energy bias. Nothing is energy is not at all important here. So why this particle is going to the left? So this is the diffusion. This is what observation is, right? That if you confine, just like what I showed yesterday, when it was half filled, and then poke a hole, and then particles go and fill the box. It's same thing happening here. But what is the benefit of the system by doing so? You can say entropy is increasing. That is fine, because now we know entropy is increasing. Entropy is, helping it. Again, we start from the beginning, actually, the movie. This is a GIF, so it is going on. So my question is that why it is going at all? My answer to that is because there are options. Because particle now has option either to go to the left or to the right. It has two choices. Of course, in a box itself, there are many choices. We are not considering that. But given that at least overall there are two choices, 210 particle has two choices, to go to the left or to the right. Now, let's understand that. So N1 equal to 105, half of the particle will be the maximum, right? So let's say all the particles, if they were on one side of the box, how many ways they can arrange themselves? So it's a combination problem, right? I have two boxes and 210 ball, all of them in one box. How many ways I can arrange that? 200 C 200, which gives me 1. So W will be 1. But see, if I give half of the particle on the left hand side, what will happen? This number of W will become 9.5. Actually, I think my slide arrangement is slightly bad, because I will show you later that W is basically NC N1. Out of N particle, I am putting N1 particle on the left hand side of the box. And how many ways I can do that? Now, if I put 0 particle, then W will be NC0, which is 1. If I put 1 particle, it will be NC1, which is N. And like that. And you can see that when W equal to NC N by 2, it will be the maximum. One can derive and show that. So if the half of the particle goes to the left and half of the particle remains on the right, the W becomes maximum. And if W becomes maximum, you know that entropy will become maximum. So if you let the system be, then what will happen? After it reaches equilibrium, you will find that 210 particles has been split equally, almost equally rather, on the two boxes. And you see this graph shows their number, and the graph will be equal. They have to be equal, and they'll be fluctuating a little bit. See, whenever they are going away from the equal value, they are going against entropy, because W will be decreasing. But that is instantaneous. On an average, it will remain always, half. So that's what I'm showing, that S equal to 0, because if W equal to 1, then ln W is equal to 0. So S is going from 0 to this much value, which is 142.66 kb. So this is what is meant by when a system is left to itself, it goes towards maximum probability or goes towards the most probable distribution. That I'll come to that. What is distribution? Again, okay, so yeah, yes. So in this particular case, there is a bias. What does it mean? In this particular case, this box has lower energy than this box. So particle will prefer right-hand side box more than the left-hand side. It will not prefer them equally. Earlier case, there was no energy bias. So they were going equal. Now see what happens? Now it has energy bias. So now it prefers the right-hand side box a bit more than the left-hand side box. That's why you will see at equilibrium, this bar will be slightly higher compared to that bar. This is the starting of the movie, and once it reaches equilibrium, that will be slightly higher. Okay, so now I'm going to talk about what the distributions is. So you see here also I have taken particles, few particles and two boxes. This is called like a two-level system. N1 number of particles are on the left hand side, n minus n1 on the right hand side. Okay. Now let's say n equal to 8, a small number. Let's say. So n1 can be 0, then n2 has to be 8 because total number is 8, and w will be, what is w again? nc n1. You can do a calculation yourself and you will see that w will be 1, a small number. So this is also one distribution. Now second distribution, how it is possible? 1 on the left, 7 on the right, and it will give the w 8. Then 2 on the left, 6 on the right, it will give w 28. And you see it will keep on increasing till you get this one where you have 4 on the left, 4 on the right, 4 on the left, 4 on the right, giving you w equal to 70. This is the most probable distribution. So these are all 8 distributions, right? So there are 8 distributions when n equal to 8 for this two-level system. In which the distribution in which particles have half-half is the most probable one. And you will see later on that Boltzmann distribution is nothing but the most probable distribution. It does not require all the distributions. So all are W's, okay? So total number of W is basically this one plus 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 all. So I can say 1 plus 8 plus 28 plus 56 multiplied by 2 because it's symmetric plus 70. This is the total number of W. But you will see that it is enough to consider just this 70. Because this is WMPD, most probable distribution. So the statistics and everything will be governed by that, and we need to calculate this most probable distribution. Now, why most probable distribution is important, I'm going to show you once more. So here I have taken n equal to 10 particle, and this is n1. This is n1. So you know that n equal to 5 will have W will be maximum, correct? And what is the standard deviation? This much. For n equal to 10, it's a big standard deviation. Now let's go to n equal to 100. And what do you see? Number 50 has the most number of W, and the standard deviation has become narrower. Go to n equal to 1000. It is even narrower. 10 to the power 4, 10,000. Now you see 10,000. I have not gone to 10 to the power 23. And even then it looks like, so what will happen at 10 to the power 23? It will be just like a line. So only most probable distribution will survive and nothing else. And you see so this is 10. This is like, this is the W by WMPD. That is what we are checking, that how much deviation is there. So you see the standard deviation for 10, this is 100, 1000 and 10,000 is very narrow. So narrow that I can even show in this plot. So I have taken another one. You see for 10 to the power 6, 1 million particle, a deviation of 0.002, 0.002. What is the probability of that deviation? 40%, 0.002. 0.2% deviation has a probability of 0.4. Now that is only 10 to the power 6. Now what will happen? Yeah, I have written already 0.2%. Now when you have 10 to the power 23 particle, the deviation of 0.000000002% will fall to 4.2 10 to the power minus 18. Just imagine. So how small that deviation is, the standard deviation, because that's what matters, right? That all possible W's and most probable W. So what is the point of all that? The point of all that is S equal to KB ln W. In fact, it is actually equal to KB ln W MPD, most probable distribution. So this is the point of saying all that although there are many possible W's are there, you just need to calculate only the most probable W. And this is again done in Mathematica to showing that as the number increases, it becomes smaller and smaller. The same thing that I already shown. So now I'm going to show you statistically that why heat transfers from high temperature to low temperature and not the other way around, and why that will increase entropy of the system. Now, when you consider that, you need to consider a simple system, just like two-level system. Here also I have taken a two-level system. It is again from molecular driving force, which I mentioned in the first day, one of the references. So you have a two-level system, 0, and this two-level means there are two energy levels here, 0 and epsilon, and there are 1, 2, 3, 4, 5, 6 particles are in the ground state with 0 energy, and 4 particles are on the excited state. So what is the total energy of the system? 4. And what is the number of particles, the number of W? 210. How the 210 came about? So because see, all the particles are distinguishable, right? And energies are of course not. So you have to apply 10. Sorry, this is automatically coming. So 10 W equal to 10 C. I have to take 4. 10C4. So 10C4 will give you 210. That's why you are getting 210. Now let's take another system, which is a low temperature system. And again, I told you, right, that heat and energies are similar. So although we are taking energy, you can think of that as a heat. So this is a low energy situation where you have only 2 particles on the higher level, right? So here W will be 10C2. So WA is 10C4, which is 210. So entropy SA will be KB ln WA. So KB ln 210. Okay. What will be the WB? KB ln 45, which is this. Now, what will be the total entropy then? KB ln SA plus SB. So KB. Okay. So here is the important thing. I'll tell you. So what is the important thing? Why ln is required? Let me see if I can stop the automatic transition. Slideshow transition. I think there is no way. I think slideshow view design. No, I think there is no way. Okay, no problem. Okay. So yeah, you see that number of states. See, for example, when you throw a coin, what are the number of possible outcomes? 6. When you throw a die. So number of possibilities 6. When you throw 2 die together, what are the number of possibilities? 6 into 6. So you see, number of possibilities, number of outcomes multiplies. So if you have WA number of possibilities in one case and WB number of possibilities in one case, total W will be WA multiplied by WB. But entropy is additive, because entropy is an extensive quantity. So entropy of system A and entropy of system B will be added together, SA plus SB. Now, something you want to add and something you want to multiply, it is only possible if you have ln in between. Because ln of a product will give you the sum. So you see what is happening there. So SA plus SB is ln WA WB is giving you 9450. So this is our initial system. Okay, these are the A and B systems which are separate from each other, having energy 4 and 2. Now if you put them together, they have to come to equal temperature, that is equal energy. So this one will come down and one will go up. Let's see what happens in that case. So WA will become 3, UA will become 3 and WA will be 120. UA will become 3 and WA again will be 120 because they have equal energy now. And what will be the number of, what will be the entropy? So entropy SA is KB ln 120. Earlier what was the number? Earlier was 210. So entropy of A has reduced. Entropy of A has reduced from 210 to 120. And entropy of B has increased from 40 kBln 45 to kBln 120. So one has decreased, one has increased. But overall, instead of 9450, kBln 9450, it is now 14,400. So what happened? One decreased, one increased, but together there is an increase. That's how it happens. That's why heat will transfer from high temperature to low temperature. Because if you do other way around, overall there will be, if you, let's say, transfer heat from system B to A, then also B will decrease, A will increase, but overall there will be decrease. So that is the point that one has to show. Now, in a complicated system, you cannot have such a simple number of particles, 2 level and all that. I can understand that. But the basic understanding will not change. Basic things will not change. The things, calculation may be more complicated, but concepts will not change. What is the concept then? That individual microstates and combined number of microstates. Individual W's, combined W's. That's what is going to happen from one system to another system. So more options is more entropy. One more example, which is, let's say, volume expansion. So again, it's from Dill's book. So what they have shown is that, let's say there are 3 balls and 3 boxes, distinguishable boxes, as you can see, and indistinguishable balls, whatever, but either way. Now, let's say if you only have 3 boxes and 3 balls, so there is only one possibility. There is only one way to arrange them. But once you have one more empty space, then there are 4 ways to arrange them. Because you can have any of these 4, boxes empty. So there are 4 possibilities to arrange. And here, there are 3 ways. 2 of the box, 2 out of 5 boxes will remain empty. So you can say either 5C2 and 5C3 both the same. So 10. You see, so as and when the more and more empty spaces increases, number of possibilities increase, and therefore entropy definitely is going to increase. So this is a very simple example. Mixing of gases. Again, very simple example. Let's say I have this situation, one gas, another gas, black color, red color, and they are in this, right? So what I'm going to do, I'm going to mix them. So initially W is 1 because this is the W for the left, this is the W for the right. I have to multiply. Now here, what is the W for the left? It is 4C1 multiplied by 4C1. So it's going to, or 4C3, whatever, same number will give you 16. Now I put 2 particles. Now it is the best situation, right? Mixing is half-half, right? So what will happen? 4C2, 36. And then this will have higher number of W's, so therefore higher entropies, and therefore this is what is going to be favorable. And then when you combine them together, then it is even more. Then it will be, there are like 8 boxes, and in 8 boxes you have to just put 4 particles, so you can choose in multiple ways. So now, just now we talked about 2-level system. Now I'm going to talk about multi-level systems. So the same concept can be now taken to multi-level systems. So in multi-level systems, I'm putting R distinguishable balls in N boxes. Okay. So again, what happens is that first I take let's say I have like so many boxes, box number 1, box number 2. So let's say this is N1, this is N2, this is N3, this is N4, and all that, right? So I have n particle. So I choose n1 particle from n particle in this many ways, and I put it here. Then I will have n minus n1 particle. Now from that I choose n2 and put it here. And then I will be left with this many particles. From that I will choose n3 and put it here, and it will continue like that. And once you do that calculations, you are going to end up with this formula that it will be n factorial by n1 factorial, n2 factorial, n3 factorial. So in general then, W is nothing but n factorial by product. So this is written as product of I in I factorial. And I goes from whatever 1 to R. R is the number of levels that one can consider. Okay. So this is called multinomial distribution. The previous one was binomial distribution. This is multinomial distribution. So I'm going to show again example of 10 particles in 3 boxes, and the statistics will not work great, as you will see that 10 particle is nothing. Ideally, it's supposed to be 333, but 334 or 433. That will be the most probable situation, but it doesn't happen that way. Okay. So we'll directly go to 210 particles. Now it should be 70, 70, 70, right? There are 3 boxes. Again, equal number will be most favorable. So let's see what happens with time. So the bars below, they show the number of particles in each boxes. So as and when there is change happening here, this is changing here. Yeah, sometimes there is a lag in the movie, but hopefully it will be okay. Yeah, so more or less I think it's fine. So you start with the 210 particle, and you have to reach. No, this is not correct because this is a 3-level system. So I will just change it. This is not correct. 1 second. So you will reach n equal to 70, and then correspondingly these calculations are not right. So basically 210 factorial by 70 factorial, 70 factorial, and 70 factorial will be your most probable distribution. You see, any combination of n1, n2, and n3 is a distribution. Out of that, the distribution that gives you the maximum value is called most probable distribution. And when they are all equal number, will give you the most probable distribution. Okay. So now let's make it more concrete. So till now I did not talk to you about energy at all. I was just talking to you about 2-level system and the number of possibilities and all that. Now let's bring in energy. Or energy I told you in a very brief manner, but now let's bring in energy and see what happens. So let's say I take 3 distinguishable particles, and there are 4 energy levels, and total energy is fixed at 3. So you can see I have so many different ways to distribute them. I can put 2 particles at level 0 and 1 particle at level 3. I will get same energy. Even if I distribute like this, 1 particle here, 1 particle here, and 1 particle here, I will get same 3 units of energy. And if I put all of them in the same level, then also I get the same energy. So what I am doing here is that my number of particles is fixed at 3. My total energy, which is E, also is fixed at 3 units. So this is the constraint that I have. Using that constraints, I am creating new distributions and trying to calculate the W for each of them. Here the W equal to 3 because any one of them can come here. Here the W is 6 because any one of them, so there are 6 possible ways because we choose any 3 for this system, and then out of remaining 2 I can choose for this level, and the rest will go here. So number of possibilities will be 6, and here I have no options. I have only one way to do it, and that's why the W is 1. So what is the most probable distribution here? 6. Total number is 10, but most probably 6. So now relative probability of those distributions is like 3 by 10, 6 by 10, and 1 by 10. So in which this one is, you can say that this is our, I showed you earlier, right? WMPD by W. And this one was, like a delta function when we had huge number of particles. Again, I'm telling you for this, this statistics will not work so great, but this is how you can calculate the statistics. That's what I'm trying to show. So, yeah, so this is the same thing. So again, I'm more clear here, Ni equal to L and NiEi equal to E. So number of particles multiplied by the energy level of that particle where the particles reside. If I combine, then I will get that total number of particle and total energy E. And this is what I'm doing it. I've already shown it. Now, when I plot the distribution, what I'm going to see, in this case, all the three are in the same level, level 1. Rest distribution is 0. So what is the distribution? This is the energy distribution. So what is the energy of each level, right? Now you see here our particle, so not particle distribution. So energy distribution, both you can say. So what is happening here? Here the distribution is that two particles are at a level, yeah, right. So yeah, so this is, I think 0, 1, 2, 3. This is okay. So you see here, this is, I think this is wrong. This should be 3 units, right? So this should have been, I can change that. Okay, I'll cut it. So this red particle should be here. I can color as red. Red particle should be here. So you see, now there is an equal distribution. In this case, there is an equal distribution in this particular case where each particle occupies a certain energy level. Here, there is very unequal because every level is empty except one particular level. And here, it's an intermediate situation where two particles are in one level, two particles and one particle is in the level 3. So you know that W is 6 here, W is 3 here, and W is 1 here. So entropy of this state is maximum. Yes, is maximum here. Now what is happening? Why S is maximum here? Because W is maximum. And why W is maximum? Because the distribution is flatter. In all the three cases, there is the same energy. But nature will choose to distribute the energy equally among the particles. And that's what I meant on my first day, that for the same amount of energy, when it is distributed in a different way, the entropy will change. And a spontaneous process will always favor a flatter distribution of that energy in order to maximize the entropy. So again, entropy is nothing but change in the distribution of energy. And there is a formula for that, that I'm not going to, which is minus KB pi ln pi, where your pi is the probability of the particle being one particular state. So now I'll show a little bit more examples of multi-level systems. So here I'm taking total energy to be 5 and total number of particles to be 4. So this n equal to 5 and this is equal to 4. Now how many possible ways you can see? Each of them is a new possible ways, and for them I get corresponding W's. Here, we get 3 most probable. All of them are equal here, again because of the less number of particles. But you can see clearly that if the W is less, the distribution is very sharp. That means here 3 particles in one and only 1 particle in the high level, and nothing else is there. Nothing else is occupied. These 3 are the more or less flatter distributions or more or less equal type of distributions. Okay. So if I increase the number a little bit more, in total number of particles 9 and total energy 7, then I will get many more distributions. Actually, one can show that I will get 15 possible distributions, and that will give me different W's for each of them. Again, how I am calculating the W? N factorial by N1 factorial multiplied by N2 factorial and all that. And you notice here is that this is my WNPD, most probable distribution. Okay. So I have not discussed here the partitions, but one can use partitions to show that if you use partitioning 7 in 9, then you will be able to get 15. You can look at my NPTEL lecture for that. And total number of possible microstates one can get using a star bar kind of formula. You can look at star bar formula, star bar distribution, and you will be able to get the total number of microstates for this kind of systems. This W I already mentioned, and this is again the number of distributions and total number of microstates in this kind of systems. I think this is just a repetition, so I'll just quickly go over it. This is just showing how it will be distributed. Now, thing is that, so we talked about 3 particle and 3 units of energy, then 5 particle, 4 units of energy, 7 units of energy and 9 particle. But can you continue like that? That is the first thing. Do I have to calculate this way, the W? Because it will be more and more complicated with time, right? With larger and larger system. Secondly, how do we even know the energy levels? Now, in this case, these distributions are possible because each energy levels are equally separated, very nicely arranged. So number of possibilities can be calculable. And how do we know whether energy is, equally spaced or not? That's what I meant, right? So even when, and how do you even estimate all possible microstates? Okay, so before I address that question, you can see that if I calculate the number of particles by total number of particles for each of the 3 cases, I will get this kind of graph, which can be fitted to this kind of equation, exponential equation, all of them. A e to the power minus B Ej, and you will see later on that this B is nothing but 1 by kBt, and Ej is the energy, giving you Ni by N is equal to A e to the power minus Ei by kBt. And this is nothing but the Boltzmann equation. So here, by doing simple statistics, by putting particles in different levels, we arrive at Boltzmann distribution. This is what our Pi is. Pi is the probability of finding particles in a certain level, and that is associated with energy. That means if the energy is higher, that means positive, then the probability will decrease. If energy is lower, that means lower or negative even, then this probability will increase. Okay, so yeah, so this one is fitted to similar equations. So B and A, B corresponds to 1 by kBt, and A corresponds to some, the factor, outside factor or coefficient. That also one can show. So now I'm coming back to that situation that even in the particle in a box, our energy levels are not equally spaced. So therefore, I cannot even distribute particles here the way I was doing it. Forget about any other complicated system. Even the simplest possible quantum mechanical system that I can solve, there itself I cannot distribute the particles. So what to do? So in this situation, Boltzmann distribution comes to our rescue for 2 reasons. One is that we have to only calculate most probable distribution, that we already know. We only have to calculate most probable distribution, and we can show that most probable distribution is nothing but Boltzmann distribution. Most probable distribution is nothing but Boltzmann distribution. And how do you know that? See, each time we are taking different particles and different amount of energy, right? And we were trying to find what is the W. Now, if I maximize W, if we maximize, I should, one second. If we maximize W, that's what we're trying to do. In general, maximize W with the constraint that N, total number of particle, and E, total energy, are fixed, we will get Boltzmann distribution. Okay. So maximize W means we are trying to find the most probable distribution, and under the constraints of total number of particle and total energy, and we will arrive at the most probable distribution. And then we don't need to look at all possible distributions, because we know that for large enough particles, most probable distribution is the one that we want. So this derivation is from Atkins, and this derivation you can look it up if you are interested. But again, as I said, it's not required for BSc level, I guess. Not required, and it's simple enough to follow. On the silence approximation, if you do, then you will be able to. The point is that how do you get most probable? How do you get Boltzmann equation? That is what is most important thing. You are getting most probable. You are getting Boltzmann equation by maximizing the number of microstates for a particular distribution for given two constraints. The total number cannot be changed. Total energy cannot be changed. Remember, that was our macroscopic condition. N, V, and E should be fixed for isolated system. N, V, T should be fixed for canonical system or for closed system. So similarly here, fixing those macroscopic constraints N, E, we are trying to see that what distribution will give us most probable W. And that distribution, if I get, then I will be able to calculate my entropy. And it turns out that that distribution is the Boltzmann distribution. So we don't need to know all possibilities. We only need to know what the energy of a particular state is. And based on that, and temperature, and based on that, we'll be able to say that what is the probability of occupying that particular level. So that much, important this is. So again, when you do that, we fit that to this equation and we get that. So Boltzmann distribution also indicates that if energy is lower, it will be more favorable, just like I showed in one of the biased example. If all energies are equal, then they are all equally probable. That's what it shows. Because if all E's are same, then the probability is same for all of them. So probability is Ni by N, which is A into e to the power EI by KBT. Now let's say E1 equal to E2. Then N1 by N will be equal to N2 by N will be equal to E by E1 by KBT and E2 by KBT. But if E is lower, then it will be more probable. And that's what I'm going to show here. So they get three boxes. The right box has lower energy. So it will be more favorable compared to the middle box, compared to this thing. So I start with middle box 200 particles. I want to see what happens when the equilibrium is reached. So right now the simulation is going on, and soon we'll see that it will be like following a Boltzmann kind of distribution, like little bit like this. Okay. See, that's what is happening. This one is having maximum probability, maximum number of particles, then less and then less. But remember, if you increase the temperature, then those biases will be gone again. Because the temperature, if is increased, this difference will become smaller and smaller and less important. So then we'll try to balance it. And that is what I'm going to show here. So when I do that, even though there is a bias at higher temperature, they are becoming flatter. So Boltzmann distribution is working, and these simulations do not consider any interactions or anything except that interaction with the box is -5, not among the particles. So even for complicated ones, it works, and that's what even experimentally one can show that. So you see today that that entropy basically is nothing but logarithm of options, logarithm of number of microstates. And that number of microstates can be calculated for simple system in a simple manner, the way I showed. More complicated system will require, let's say, simulation someone can use to find out. and many other techniques. But directly W nobody calculates because we only want to find out most probable W, and that can be found out by finding Boltzmann distribution. So basically, if we know the energy levels, we already know what will be the W, or most probable W, because that's how it will be arranged. And once we know that, we will be able to calculate the other properties. Okay. So these distributions or Boltzmann distributions, I forgot to mention that it is for distinguishable particles, where energies are not distinguishable. So it is distinguishable particles, distribution of distinguishable particles in indistinguishable boxes kind of statistics. But there are other kind of particles which are not distinguishable. They are called bosons and fermions. They are not distinguishable. So Boltzmann statistics will not be able to apply there. Only the Bose statistics and Fermi-Dirac, Bose-Einstein statistics and Fermi-Dirac statistics will apply. And I can show you in a very, very simple example that how those statistics will come. So for example, right now I have made all the particles colorless, like same color, not colorless, like all blue color. And there is a condition again for bosons and fermions that any number of particles can occupy any level for bosons, whereas for fermions it is not true. So when I do that and distribute total energy phi among 4 particles, then I get some W's. Here again, exchanging particles will not make much of a difference. So all W is basically 1. And then I calculate the overall the number of W's at each level, and I get this probabilities for occupying a particular level. For more number of particles, I again have some statistics which I plot here. And when I plot them, and I see that it could be fitted to this equation. Again, these are I'm doing in a statistical manner, no derivation, nothing. It's just that I just taken the fact that particles are indistinguishable and there are energy levels equally separated, and then I just try to see that if I fit it, that what kind of distribution I'll get. And it turns out that it will follow, again, B is 1 by KBT, it will follow this particular equation, which is Bose-Einstein statistics. Similarly, I can do for fermions, but here now I have a constraint that not more than 2 particles will occupy a particular level, and in that case, this distribution will not be applied, this distribution will not be applied, and I'll get some statistics. And then similarly, when I will have more number of particles, none of those in 7 units of energy and 9 particle, I cannot get any distribution that will work, and then I'll get another distribution which I have not shown, I guess. 7 units of energy and 9 particle, and 9 units of energy and 7 particle. Yeah, 9 units of energy and 6 particles will work, and I will get some statistics by calculating overall the number in each level, and then I will see when I fit it. It will, again, the statistics is very poor right now because of the less number, but if I do it properly with more particles and things like that, I will see that it will follow this equation, which is again the Fermi-Dirac statistics. And all the 3 statistics like Boltzmann, Fermi-Dirac, and Bose-Einstein, Fermi-Dirac, and Maxwell-Boltzmann statistics at a higher temperature you can show that at a higher temperature this will actually go to the same statistics, which is Boltzmann statistics. So Fermi-Dirac and Bose-Einstein statistics are applicable for quantum systems at low temperature, and that's why they differ from Maxwell-Boltzmann statistics. And of course, they are also indistinguishable. So you see that not even going by the theory behind it, just going by the distribution of particles in different levels, one can get a physical picture of what this is and how one can get those statistics. And you understand now why it is called statistical thermodynamics, because in one hand I'm trying to calculate statistics, and another hand I'm connecting it to the physical quantity called entropy, which is a thermodynamic quantity, and therefore statistical thermodynamics is a kind of a combination of both of them, right? So with that, I think I finished it a little fast today, but this is what I had to talk about. And there are many more things that are not discussed in these 3 classes, mainly because it will require more time. You have to do more tutorial problems to understand them. That's why if you refer to my NPTEL lectures, you will see, for example, I did not talk about free energy at all, like how you are getting free energy. Basically, one can show that you can get that by Legendre transformations of energy. So if energy is a function of free variables, so I can just show you in a very, very quick manner how you are getting free energy, just in a blackboard setup, which I like. So basically, what I actually missed one thing is that the fundamental equation of thermodynamics. So this fundamental equation of thermodynamics is actually a key thing, which says that U, which is internal energy, is a function of S, V, and N. That's it. What kind of function? We are not saying. For example, if I say F is a function of X and Y. Now, Fxy can be x squared plus y squared. It can be xy or any sort of things. That I'm not saying what kind. I'm just saying that it's a function of this in this particular case. So this is the fundamental equation of thermodynamics. Now, if I expand that, the total change in energy, then I will have to do du by ds as a constant Vn ds plus du by dv at a constant S and N dv plus du del u by del n at a constant S and V dn. Once I write that, I can define this quantity as temperature. So it will be TDS. This quantity as minus P, so PdV, and this quantity as mu and mu dn. So I get this equation, and these things are nothing but definition. So what is temperature? Del U by del S as a function of V and N. And you see, U is a extensive quantity, H is an extensive quantity, therefore T must be an intensive property because it's a ratio of two extensive property. Similarly, for P is minus del U by del V, the constant S and N. U is an extensive property, V is an extensive property, therefore P is an intensive property. Same way, mu, chemical potential mu, is also an intensive property. Now, once you get U, I'll just use the eraser here. So now you define the temperature, pressure, and all that in this equation, fundamental equation. One can show that everything, all, whatever you have in the book of thermodynamics can be derived from this. So you got U now. Now what you want to do is that the Legendre transformation you can do, which says that I can write a quantity R as a Legendre transformation of U. So that is du, U minus del U by del V, V. So I am transforming the variable V into something else. Now what is del U by del V? Del U by del V is minus P. So it will be U minus PV, which is U plus PV. This quantity I define as H. Okay. So now H will not have any more SV and N. H will have SP and N. Similarly, if I do another Legendre transformation, not the V but S, will be the U minus del U by del S into S, which is U minus TS, which we know as A. And A will now have N, V, and T as a variable. Now, if I do both U minus del U by del S, S minus del U by del V, V, I'm going to get G. So these Legendre transformations, what is a Legendre transformation? It does not change the equation. It just plots a function f, which is a function of x and y. It plots another function psi as a function of the intercept c and slope, let's say m. Same information, whatever was there, it is plotting in terms of other things. Again, so this one I could not discuss in detail. but you will find it if you write them an email or in NPTEL lecture, you will find it in much more detail. So you see, so they are nothing but the same thermodynamic potential. So all of them are same thermodynamic potentials, just looked from a different angle. And once you get your G, your A, your H and all that, you can keep on deriving any of the equations. Some are definitions, some are derived quantity from other things. And I also discussed one thing called Jacobian method for partial differential equation. That also you will find in my NPTEL lecture, where such a complicated quantity like this, del G by del V at a constant S, right now I don't even know what it is, but you will be able to see, derive it in terms of 4 quantities: alpha, which is coefficient of thermal expansion; beta, compressibility; Cp, specific heat; Cv, specific at a constant volume. In fact, Cv also is not required because Cp and Cv are related. So in just in this, using this 3 and temperature, pressure and all that, you'll be able to express any thermodynamical, partial thermodynamic quantity. But that will require some time, at least 2 lectures. So therefore, I will not be able to cover it, but I wanted to give you an overview of that. Okay. So yeah. So Akshaya, you raised your hand. If you have any questions, please ask. Okay, I'm going out of this. Okay, so I think with that I will finish it and hand it over to Professor Jaman Matthew.
Yes, thank you. Let's wait if you have a question.
Yeah, so I just came to know one thing. I don't know whether I know you will remember or not. One of my PhD student told me that my former PhD student, who is now a postdoc in I think Europe somewhere, so she was a student from your college. Her name is Hridya VM, and she joined IISER Pune as an PhD student around 2014. And then she joined my group, and then now she's doing her postdoc.
Hridya.
Hridya, yeah. VM.
We were fortunate to teach her also.
Yeah. She was really good. She was really good. Actually, yeah, she's one of my best students. She was so sharp and
she's very dedicated and persevering.
Yeah, and very thorough in her approach.
Yes.
So that was very helpful. Yeah, right now she's doing postdoc. Yeah.
Even now,
very
recently also there is one student, Leo. I don't know whether you have.
Who was the name?
Leo.
Not in my group. Not in my group. Yeah. Look, I told you right the first day there are so many students here.
Yeah, we are actually a feeding institute, feeding college to IISERs and IITs, because every batch 2 or 3 students are into the various IISERs and IITs.
Right, and they are good students. Yeah.
Thank you. Yeah.
The best ones reach those institutes.
So yeah,
so it was a pleasure meeting you, sir, and getting to know a different perspective of thermodynamics. Though I've been teaching thermodynamics for quite a few years now, so it was refreshing to hear it from a different perspective. Right. Thank you so much, sir.
Yeah, I thought that anyway the standard approach it is followed in many places. So I wanted to give a different approach so that it kinds of makes the thing complete in a way, because 3 days my focus was to give only the some different thing what you normally they don't hear from classes. So that's why I took this approach actually. So and you saw that how few equations I use. So I think people are afraid of equations.
No, without the equations, you are able to get to first law of thermodynamics, which is a wonder.
I had to in some point, but yeah, minimal amount. Yeah, that is
yes.
So any questions?
Yeah, even if they have questions later on, if they don't want to ask now, I'm fine with that. The email is fine. You have been sending me, and they can also directly email. My website I have already shown, so they can search and send me an email. I'm okay with email actually, so I can always reply. Not a problem. And also, as I said, that if they're interested in a topic and have questions, they can in fact ask anybody in IISER, any faculty, and I'm sure if the question is kind of relevant and to their domain of knowledge, then they will definitely reply, as far as I can tell. So. Now, sometimes students think that they are afraid to approach a faculty, right? They think that what that they will do or not and all that. But that is not the case. That's what I'm trying to say. That it's quite okay to ask a question, and just remember that all of us were like you guys at some point, right? So we have gone through all those days and situations where we were also afraid to ask questions to professors, thinking that what they would think. But thing is that you have to be genuine. That is true in the question, and as long as that question is coming from genuine interest, that is it's all right. Then the question does not matter.
So if some students can feedback, that would be nice.
Yeah, so if you can get the feedback, at least it will be helpful to me because
yes.
And
actually we have given a feedback form in the chat box, so students can
let them write an honest feedback regarding the label, regarding the delivery, so that it will help me in future also to we take feedbacks from our classes a lot, and actually the day of the feedback is our examination day before day. So we all eagerly wait for the feedback, and we talk about the scores and comments and all that. That's a kind of a fun day for us.
Yeah, feedback form is shared in the chat box. Students can fill it, and we will some.
Okay, sure, definitely. So that's all, I guess, right? So
seems no questions.
yeah, I guess no questions today, but that's fine. So maybe they will ask through email.
Yes, and even especially I think in BSc level, they are not learning statistical part much.
Right. No, I understand that. No, I understand completely. So I will share the slide. Let them go through them slowly. See, I understand that a different thing takes time to absorb. These things should not be taught in one class. It should be taught in multiple classes. But if I don't cover them, I will not reach anywhere. So I had to cover the minimal portion that is required for delivering the point.
But the major portions are all covered.
Yeah. So if they know that there is something called KBL and W exists, and W can be calculated, most probably W is the important one. And my thing is solved.
All the probabilities have also been discussed.
So, anyway, we have recorded all this class, sharing that as a YouTube channel. It's public, so everyone can watch. Right. Many attendees they are having exams these days, so many students are not attending because of that. But they will watch it later on, and they will learn, and that's what we see from its view. Many are watching this.
Sorry, I could not hear the last part.
Many are watching these videos
at
night.
Definitely. So, you can always write to me my email address, and then I will, if I can, I will definitely reply back to those questions.
So it was very nice to hear from you for the last 3 days. We had a really wonderful session on thermodynamics. So thank you so much on behalf of our college, Joseph College. We thank you. I mean, this is one of the best parts that came out from the pandemic. Although that was trouble, but this is one of the best things that we could get many of
Right.
great persons like from different parts of India, and they can teach our students.
Yeah. I think there will be many more lectures like this, right? Many more.
Yes. We will be covering almost another 8 more topics. So next week we will be having a two days,
Right.
and Friday class on chemical kinetics by Dr. Jatish Kumar from IISER Tirupati. So that will be the second session.
Yeah. So I urge all the students to really, prepare yourself for this. Make this, opportunity. Make use of this opportunity because this is something that as a student we never got because our time internet was not that great. Nothing was in the tip of our finger. And if we had doubt, we had to depend on library books and then catch hold of seniors or, some teacher, at the list, of course, the last resort. But that's how we did it. So now the opportunity is there and to make use of it so that in future, you will remember this thing a lot. Even now, as a scientist or as a researcher, we listen to others talk to learn because that never ends. Learning never ends. So now the conference is starting tomorrow. So that's why we shifted, right? So many talks will be coming and we'll listen to them and we'll try to understand as much as possible. And that's how it goes. So it is also okay not to understand fully because none of us understand it fully. Because if we understood, then we would not do anything out of it. Like we'll not have any curiosity to know more. So only when your understanding is halfway through, you have the highest curiosity. Just like entropy thing I explained. If you know fully, then you will have a detachment. If you don't know anything, you will have a detachment. But when you know a little and you want to know more, that is when your curiosity increases. And all these things will just to instigate that curiosity. So why I even didn't even try to explain because I thought that if you're curious enough, you will now take a initiative and try to understand a bit more yourself.
So we have a wonderful start to our student enrichment program. Yeah, thank you very much.
Thank you very much. And again,
and we look forward to your association in future also.
Definitely. And
hopefully you will be able to make it to the Devagiri College when the COVID situation improves.
I have been to Trivandrum many times, IISER Trivandrum many times. So yeah, definitely. If I get an opportunity, then I would love to come there.